Hello, everyone. So I'm Raducan from Imperial College London, and today I'm going to talk about our numerical simulations of the Dart impact and why, from a numerical modeling point of view, we need a Hera mission. And you've seen quite a lot of presentations today about Dart and how it's going to impact the Moon and deflected by an amount that will be detectable from the Earth observatories. And today we're going to talk quite a lot about the momentum enhancement, beta. And again, you've seen from Angela's presentations and the other presentations that we can determine beta from the ejecta. So I'm not going to go into that more. I think to remember is that basically the larger the beta, the more deflection we can expect from the Dart impact. However, we do know that beta depends largely on the target material properties. And we know that from laboratory experiments and from numerical simulations. And unfortunately, we do not know exactly what to expect from the Moon. So we use the ICL shock physics code to model the Dart impact in 2D and 3D, and in trying to determine this beta factor. And for the whole presentation, all the simulations I'm going to talk about today, we use the same impactor parameters. 300 kilogram aluminum sphere impacting a basal target at 7 kilometers a second. And firstly, we are going to look at comparing ICL simulations in 2D with 3D simulations. And that is because while 3D simulations are a lot more realistic, they're also a lot more computationally expensive. And just to give you an idea, using the same resources, we can run about 20 2D simulations in the same amount of time. We would run one 3D simulation and at a much larger spatial resolution. So the first scenario we modeled was the Dart impact into a 10 kilopascal target at 20% porosity, a vertical Dart impact. And we can see here the results from the two simulations. And here is the cumulative ejected mass normalized by the mass of the impactor as a function of ejecta velocity normalized by the velocity of the impactor. And we can see that the two simulations match pretty well. If we integrate the area under the graph, we get the cumulative ejected momentum normalized, which is the value here is beta minus 1. And we can see again that the two simulations match pretty well, which is good news for us because it means that we can use 2D simulations to accurately predict the beta value for a vertical impact. However, the Dart impact is most probably not going to be vertical, and it's going to be instead at an oblique angle. So next, we look to compare our 3D vertical simulation with an oblique 45-degree simulation. And we have here 4 snapshots at 4 different times of the surface topography of the two craters, and the upper row is the vertical impact, while the lower row is the 45-degree impact. And we can see that in the early times in the oblique impact, we have highly asymmetric ejecta, that it gets more symmetric as the crater grows, which poses the question, in which direction will the asteroid actually move if the ejecta is highly oblique? And to answer this question, we look at the momentum from these two impacts. And here is the vertical impact, and here is the 45-degree impact. And colored in purple is the impactor momentum. Then we have in this bluish color, the momentum enhancement vector, which is in the opposite direction with the momentum of the ejecta, and it has the same magnitude. The sum between the momentum enhancement and the impactor momentum is going to be the target momentum, and it shows basically in which direction will the target move, and is colored in black here. So we see that in the vertical impact, all 3 vectors point perpendicularly downwards. However, in the oblique impact, we have the impactor momentum pointing at a 45-degree angle, the momentum enhancement pointing at an oblique angle from a different direction, and then the target momentum, the one in black here, pointing downwards, but again at an angle. And then what we have underneath are 2 graphs showing the cumulative ejected momentum again, which was beta minus 1 from the 2 simulations. And to note here that in the oblique impact, we normalize the ejecta momentum by the vertical component of the velocity, of the impact velocity. And then we see that as the crater grows, the ejecta in the oblique impact becomes more symmetrical. And surprisingly, we end up with a target momentum that points almost vertically downwards. And then interestingly, if we are looking at the cumulative ejecta momentum, we get the same value. And again, this is normalized by the vertical component only. And a lot more tests are needed to draw a conclusion from this, but it would look like we can still use 2D simulations to tell us about the vertical component of the momentum. And that was good news because, as I mentioned, 2D simulations are require a lot less computational power to run. So for the rest of the presentation, we'll use the ICEL 2D to model the DART impact. And because we don't really know what to expect from DD-Moon, we modeled 3 possible target scenarios. And the first one was a homogeneous structure for which we systematically varied the cohesional strength and the porosity of the target. But then the target might not be homogeneous. So we also considered a target that has a layer structure. And this is very similar with what we see on the Moon. So it's basically a weak porous layer overlying a less porous, stronger substrate. And we considered 4 combinations of porosities for the upper layer and for the substrate. And then for each porosity combination, we varied the thickness of the upper layer, which we will call the regolith. However, we've seen from other asteroids that the transition between this upper layer and the lower layer might not be as sharp as on the Moon, but instead it could be more gradual. So we also looked at simulating impacts into a target in which the porosity increases exponentially with depth. And again, we considered 2 porosities combinations. And for each porosity combination, we varied the e-folding depth, which is basically how sharp the transition is. And because we are short on time, I'm going to go directly into the results. So we know that we will measure the change in velocity from the Earth's observatories, and from that we can determine a beta value. But the question is, if we have a beta value, could we then go back to our simulations and point out to what simulation predicted that value, and as such infer the target material properties? And let's assume we measured a beta of 2.9, and this is just a randomly picked value. What is the simulation that actually predicted that value? And if we look at the results, well, that's kind of complicated because there are a lot of simulations that predict that. So if the target is homogeneous, and here is a graph showing beta as a function of porosity for 4 different cohesional strengths, we can see that we can either get like an impact into a 10 kilopascal target at 10% porosity, or maybe a 1 kilopascal target at 30% porosity, or even a 0.1 kilopascal target at 50% porosity. Looking at beta alone, we can't really tell which one it is. However, these craters form different crater sizes. So if we know also the crater size and the beta value, we would potentially go and look at the simulations and pick the correct porosity cohesion configuration that produced that beta value. And if the target is homogeneous. If the target is layered, and these simulations are very interesting because we end up with crater profiles that look very different. For very thin regolith layers, we end up with what is called concentric craters. For slightly thicker layers, we get flat floor craters, and then there are central mount craters. And then for very thick regolith layers, we get craters that resemble a crater into a homogeneous target, and there are the bowl-shaped craters. If we look at the beta value, and here is plotted as a function of the regolith thickness for the 4 different porosities configurations, we can see that beta alone is not going to tell us much about the layer structure. If we also know the crater size, that also doesn't help too much. However, these impacts do have different crater morphologies. So if we know the beta, the crater size, and the crater morphology, that would give us an insight into this type of target. The last case we looked at was the targets in which the porosity increases gradually with depth. And here the things are a lot more complicated, because we see that beta as a function of the e-folding depth doesn't vary very much, and neither does the crater radius. And all the craters formed are ball-shaped. So to get any insight into this type of impact, we also need to have a density estimate of the target. So to validate our numerical models, we will need the morphology and size of the dart crater, a bulk density estimate, a NASTRI surface survey, and maybe a surface cohesion estimate. And then luckily for us, ESA's Hera mission is planning to do just that. Hera will arrive at Didymoon several years after the DART impact and perform the detailed measurements that we need to validate our numerical models. However, Hera has not been approved yet, so hopefully it will get approved, because it's really crucial to have these measurements. So we've seen that 2D simulations can be accurate enough to model vertical impacts, but we need more testing to see if we can also use them to tell us about the vertical component in an oblique impact. We've also seen that beta varies a lot with cohesion, porosity, and the target structure. And we can get values anywhere between 2 and 4. But I want to emphasize here that cohesion is really important. And if the cohesion is anything that we like what we see on Bennu and Ryugu, then we can expect even higher beta. So for numerical models, we really have to go really low with the cohesion. But then we also seen that we can have the same beta values from a variety of targets. So to take full advantage of this amazing experiment that is DART, and to validate our numerical models and to transform the data from DART into a repeatable and well-understood experiment, we do need the Hera measurements. Thank you.
Time for a few questions.
Pete Schultz, Brown University. I was very happy to see the effect on the diameter of the crater in the upper regolith model, because we did some experiments, published it a while ago, that showed that, in fact, the diameter of the crater in the regolith doesn't make any difference because of the regolith thickness. It actually acts as if it's a complete half space.
Yeah.
So in other words, it's beautifully validated with the code, in spite of the fact that you may have a layer that could transfer the energy along that interface. That doesn't seem to be what's going on. So it was very nice to see how well that matches. It only needs about 2 times the projectile radius to maintain that diameter. Yeah. So you can actually estimate the coupling based on the diameter of the crater in that outer layer thickness.
Yeah.
Anyone else? All right.